In this video, we'll learn how to compute the surface area of some surface, and that's given to us by a vector function of two variables. So let's assume that we have a smooth surface S given by the vector function ruv, okay, with components xuv, yuv, and zuv. Such that u and v, the pair uv, varies over some domain in the UV plane. Then the surface area of S is the following, is given by the following double integral. So the surface area A of S is the double integral over this region in the UV plane d of the length of the cross product of the partial derivatives of this vector function ruv. So you compute the partial derivatives of ruv with respect to u and v, take the cross product of these two vectors, compute their length, and that's the function of u and v that you want to integrate over the domain D. So this result, well, this comes from the fact what we've seen before is that each small area element on the surface can be approximated by the length, by the area of the parallelogram that's spanned by these tangent vectors ru and rv, and the length of that parallelogram is the length of their of the cross product of these tangent vectors, and that is why we find the surface area via this integral. So to give you an example, let's compute the surface area of a sphere of radius r. So find or compute the surface area of a sphere of radius r. This radius is fixed, it's some positive number, capital R. So use spherical coordinates and to formulate your vector function, and use this formula to find the surface area of such a sphere. Input your answer below. Okay, I hope you pause the video and put your answer below. So we all know that it's 4 pi r squared, but how do we get that result? Well, r now depends on the spherical coordinates phi and theta. So I said you should use spherical coordinates, and so there the x component, well, I should say that we want this sphere to have radius r, so the radius is fixed at r, capital R, but phi and theta can change in their respective intervals. So the x component is r times the sine of phi cosine of theta. The y component is r times the sine of phi sine of theta, and the z component is r times the cosine of phi. This you may remember from the formulas in spherical coordinates that we had. So this is our x, y, and z components for this vector function. We have to find the length of the cross product of these tangent vectors. So we have to differentiate r with respect to phi and theta. So let's start with differentiating it with respect to phi. So each component we differentiate with respect to phi. So this is r times the cosine of phi, cosine of theta is the first component. Then we have r times the cosine of phi, sine of theta, that is. And the last component is r times minus sine phi. When we differentiate with respect to phi. So similarly, we can differentiate with respect to theta, each component, and that gives us minus r times the sine of phi, sine of theta. For the first component, we get plus r times the sine of phi, cosine of theta. For the second component, here there's a j missing. So and last component is giving us 0 because it does not depend on theta. When we differentiate that with respect to theta, we get 0. So there's no k component in that vector. So all we need to do now is take the cross product of these two vectors, so that you know at this point how to compute. Let me just give you the answer. So what we get is r squared times the sine squared of phi, cosine theta, the I component. We get r squared times the sine squared of phi times the sine of theta in the j component. And finally we get plus r squared times sine of phi, cosine of phi for the k component. And the length of this cross product, again, we have computed this before when we computed the Jacobian, when we looked at the Jacobian of the transformation from spherical coordinates to Cartesian coordinates. This has a length of r squared times the sine of phi. Okay, so that was Jacobian, but now r is fixed. So this is the function we want to integrate to find the area, surface area of this sphere, as phi and theta change over their respective intervals. So phi changes between 0 and pi, and theta changes between 0 and 2 pi. That's how we get the entire sphere. And this is the function which we have to integrate with respect to theta and phi. Of course, the theta integral will give us a factor of 2 pi. Nothing depends on theta in there. So that's just a factor of 2 pi that we get. Let me just pull out that factor of r squared. And all we have to do now is just integrate sine of phi with respect to phi as phi changes from 0 to pi. That's just the sine curve, the area under the sine curve as it goes from 0 to pi. So that's just a factor of 2 that we get there. So that is just a factor of 2. So all in all, we get 4 pi r squared for the surface area of this sphere of radius r. Okay, I hope you enjoyed this video, and I'll see you in the next one.